All right, so now we're going to move on to chapter 2, and it's going to be broken up into several parts. And we're going to start off with chemistry and the basics. Don't freak out if chemistry scares you, but we're going to talk about what it is, elements, and how we take these different elements and combine them together to make molecules, and how we use these molecules and these bonds that we create to drive energy throughout different processes throughout life. So let's first introduce what matter and energy are. So matter is anything that occupies space and has mass, and it can be in various states, and the state depends on how the molecules are able to move around. So the gaseous state, the molecules are very far apart, they're constantly moving, they're probably bouncing off each other. The liquid state, the molecules are in no direct bond, but they are closer in proximity. Versus a solid state, you'll probably see them be in direct bonds with each other and not moving. Now, it's important to know that all tangible substances are made up of matter. Now, matter is made up of elements. When I talk about elements, think of the periodic table. So the periodic table is broken down into 118 known elements. And what's key about an element is you cannot break it down into anything else. Like hydrogen will only be hydrogen. Oxygen's only oxygen. You can't break it down into something else. Now, the reason I introduce these two things is we have to use energy to drive pretty much everything we use for our cells as biology in general. Break a hydrogen bond when we go through DNA replication, when we grow, respond to stimuli, movement, reproduction, dividing the cell for cell reproduction requires energy. Now, how we're going to get this energy is we're going to see that in a molecule, which is what we're going to take different elements and combine them in combinations. What we're going to do is we're going to create these bonds between these different elements. And in the process of doing that, we're going to create chemical energy. And what we're going to do is we're going to harvest it by making and breaking these bonds and use it to power reactions. So let's show two different types of reactions that you'll see. You're going to see reactions that are going to give off energy or reactions that are going to take energy. So let me get my little pencil and highlight right. So first off is an exergonic reaction. So use the bold face right here. So exergonic is exiting energy. What that means is energy is going to be the process. So with this reaction to happen, which is a line right here, we're going from reactants to products, going from this to that. In the process of converting it, what we're going to do is we're going to get energy, it's going to be released. An example I use is if you ride a bike up and down a hill or just jogging. When you're going downhill, it's a lot easier. Gravity's kind of helping you. You just kind of go with it, and you just, even if you're riding a bike, you can take off the pedals and just go. Energy is released in this reaction. Now, the opposite reaction is an endergonic, all right? So entering energy. Now, with these reactions, if we compare it, to go from reactants to products, it takes an input for it to happen. So this is like climbing up that hill or riding your bike uphill. You have to keep pedaling harder and harder and harder just to get to this point. Versus the opposite one, you gained energy, you have to put in energy on an endergonic reaction. So what metabolism does is it combines both of these reactions, and they'll kind of link them together. So you might use some reactions that give off energy and some that take energy. And we're going to line them up in order to make something happen. And these are going to be called metabolic pathways. Now there's two different types of reactions. We'll talk about it. There's anabolic and then there's catabolic. Anabolic is where we're going to take small molecules and build a molecule out of it. And when we do that, it takes an input of energy. Versus catabolic reactions, which where we have larger molecules, and we break these bonds. In the process of breaking these bonds, we get an excess of energy. So energy is the output. So anabolic is like an endergonic reaction. Catabolic, think of catastrophe, blowing things up. Exergonic. So what metabolism does is it combines these two reactions together to drive other functions. So this is just like a metro map of metabolism in your cell. And it kind of looks like a subway map. And you'll see these different reactions kind of feed into each other. When we get to metabolism in unit 3, it'll make a little bit more sense. But you're going to see everything is kind of linked together. What drives one reaction, you might gain some energy, and then we're going to use that to drive a reaction that's going to take the energy. So they all play off each other. So let's break it down to the very smallest components. And if you remember the hierarchy, we started at the atom. So atoms are the smallest components of an element. And we're going to talk about the different components in a second. But depending on the type of organism you are, you're going to contain different combinations. So this is a different chart showing you the different combinations that make up you. So you can see like, okay, a lot of you is composed of oxygen. Now, if we take an atom and break it down smaller, you can break it up into 3 subparts: your protons, your neutrons, and your electrons. Your protons are going to have a positive charge, and you're going to locate them in the middle, or what we call the nucleus of an atom. So if you look at this diagram right here, it kind of resembles the solar system if you look at it. Your protons are going to be positive, marked by the plus mark, shown in the nucleus. Now, neutrons are going to have a neutral charge. They're also going to be found in the nucleus. So in this diagram, they're just shown as the empty circle. Now, when we add the protons and neutrons together, we're going to get the mass number of the individual atom that we're talking about. Now, the electrons, they're going to be negatively charged, and they're going to be very small. They really don't have a mass. And what they're going to do is they're going to orbit this nucleus. So think of this as like the sun, and the electrons are like the planets that orbit around it. Now, what molecules are is when you take these different atoms and combine them in specific ratios. So let's talk about that a little bit more, but I want to kind of show you the periodic table and how you can relate that to all the different parts of an atom. So there's 3 parts: the protons, neutrons, and electrons. Now, if you look at a periodic table, you're going to see different numbers. You're going to see a top number, a bottom number. Most of the time, you'll see an abbreviation for the element, and sometimes it'll give you the full name. Now, this top number is called the atomic number, and this is going to tell you the number of protons in the nucleus. It also tells you the number of electrons. So you get 2 important numbers, boom, the protons and electrons, from this top number. So for carbon, it's telling you that there are 6 protons and 6 electrons. Now, so you got the numbers for these 2. Now, to figure out the neutrons, we have to use this bottom number right here, which is called the atomic mass. Now, the atomic mass is the weight of the protons plus the neutrons together. The electrons are so small they really don't have a mass, but the atomic mass is just the whole mass of the individual element. So to figure out the number of neutrons, you just take the atomic mass minus the atomic number, and then that will tell you the number of neutrons. So for this carbon atom right here, we have 6 protons, 6 neutrons, and then 6 electrons. Now, as I mentioned, there's orbits. The electrons, they orbit around the nucleus. They're going to form what we call valence shells. Now, with valence shells, we just don't randomly have them. There's an order to them. And the electrons have to fill a certain shell before you can progress to the next one. So our first valence shell is going to have a maximum of 2 electrons, and it's going to be the one closest to the nucleus. Once we fill that shell, we will start to populate the next shell. And you're going to see there's going to be a magic number of 8 that's going to show up. It gets more complex the higher we get down the table, but we're going to stop at 8 for simplicity. So once the 8 electrons are filled in that shell, we move on to the next shell, and so on. And we keep doing that until the shells are full or we used up our electrons. So this is an example for magnesium. It has an atomic number of 12, so there's 12 electrons. So the first shell has the 2. The next shell has the 8, so that's 2 plus 8, that's 10. So we have 2 remaining electrons, and that will be the outer shell. Boom, boom. Now, something the book does mention briefly are isotopes. So isotopes are pretty much different forms of the same element. So right here on this diagram, I have showing carbon 12, 13, and 14. Carbon 12 is a common one. But what happens is you're going to have the same number of protons, but you're going to have a different number of neutrons. So for each neutron you get, it's going to raise this number right here. So we might be at 6, 6, but now we're at 6, 7, 6, 8. We keep adding those. So the mass number is going to reflect the extra neutrons. Now, as I mentioned, those are the individual elements. So now let's take the elements and combine them to make molecules. And how we make these molecules is we're going to hold them together via chemical bonds. So I mentioned earlier, the chemical bonds are where we're going to harvest energy to drive reactions. So by making these molecules, we're putting little packets of energy into them that we're going to take in later. So if you remember me talking about the electron shells, this is where those bonds are going to be formed. Now, the magic number was 8. So we're going to see that these electrons are going to be shared between different atoms to make these different molecules. So here's just some examples, like a water molecule, which is shown in both here, is an oxygen with 2 hydrogens. And what's happening is we're sharing electrons between this outer shell of the hydrogens and with the outer shell of the oxygen. Carbon dioxide, nitrogen oxide, here's just some examples of different molecules. So a little bit more about chemical bond facts. So if a bond's going to form, it depends on the attraction between the atoms. So we want these shells to interact with each other. So it's going to be the outer shells that are going to interact. Once a shell is full, it's not going to interact. And the opposite charges between atoms are going to drive these reactions or the attraction to each other. Now, depending on if it has room in that outer shell, if it has met that magic number of 8, will determine how many atoms it can interact, or electrons it can interact with another atom. So for hydrogen example, it only has that one shell and it's only going to have one electron, but it's going to be looking for another one, someone to share another electron with, because it wants to get to that outer shell of 2. Now oxygen, it had 6 in that outer shell, so it's looking to get 2 more electrons from someone else. So what happens is this oxygen is going to share 2 of its electrons with 2 different hydrogen molecules, and they're going to share their hydrogen electrons. So ultimately, these 2 hydrogen are content because now they have their 2 electrons in their outer shell. And the water molecule, the oxygen is not content because he now has 8. I made him a boy just for today. Now something else the book has mentioned a little bit is ions. So in ions, when an atom does not contain equal numbers of protons or electrons. So remember on the periodic table, that top number showed that ions showed that it was the equal number of protons and electrons. Well, if it happens to give or take electrons on, it will turn it into a cation or an anion. So overall, as long as everything is equal, it's going to have an overall neutral charge of 0. Now, if it gives away its electrons, it's going to be taking away. So remember, electrons have a negative charge. When that happens, its charge is going to go positive, and that's going to be a cation. Now, if it's a molecule that takes electrons, what happens is your overall charge is going from 0, it's going to go negative because you're gaining more negative electrons, and this is called an anion. So the last part kind of talks about some different types of bonds, and we're going to focus mostly on these first 3 right here. But there's also this 4th one, van der Waals, that the book briefly mentions, but we're going to focus mostly on covalent bonds, which is sharing electrons, which are the strongest bonds we're going to see. Ionic bonds, so this is the give and take of electrons. Hydrogen bonds, which are going to hold more compounds together. And then, as I mentioned, there's a 4th one, van der Waals, but I'm just mentioning it, but you're not required to know much about it. So covalent bonds. Think of sharing as caring. It doesn't rely on the charge of the elements or anything. Sharing is caring. What they're doing is just sharing electrons between each other. Now, covalent bonds, they are going to be the strongest bond, and they don't dissolve easily in water, because you're going to see on ionic bonds, which are salts, they easily dissolve and break apart. So what's going to happen is they're going to share these electrons in these outer shells. Now, there's going to be two types of covalent bonds. There's going to be either, let me highlight right here, nonpolar or polar. Now, it depends on how the electrons are being distributed. So if it is a nonpolar, all right, so we're talking about here, the electrons are shared equally between each of the elements. So everyone is being fair, you know, the distance is equal between all of them. Versus if it's polar, someone's being a little bit more greedy. Now, when that happens, it's going to lead to overall partial or positive charge in the water molecule. So we're using water as an example. So what's happening is the nucleus of the oxygen is a little greedy. So what it's going to do, it's going to pull these electrons closer to its own nucleus. Now, when it does that, it's going to make this part of the molecule appear more negative. And then since the electrons are further away from the nucleus of the hydrogens, you're going to have positive parts on these parts of the molecule. Now with these covalent bonds, they can share two electrons. They can share double bonds. There's also triple bonds. I just want you to know that the number of electrons can vary that they share. So the next big group was the ionic bonds. So remember, anion, cation, come back to haunt us. This is the give and take of charges. So remember, we're trying to get to that magic number of 8. So this is a common one, table salt, right here. So you have sodium and chloride. So if you look at the outer shell, sodium has this one single electron hanging on its outer shell. And chloride, if you count it, 1, 2, 3, 4, 5, 6, 7. It's only looking for one more to have that happy outer shell. So what are these two to do? They're going to have a great relationship, and what they're going to do is form an ionic bond. Now what the ionic bond does is this electron is going to be given to chlorine. So when that happens, they have this weak bond associated with each other, and they're going to overall have an overall change in their overall charge as a result. So due to that sharing of the electrons between the sodium and chloride, it keeps them loosely associated. Now these are going to be easily dissolved in water compared to the covalent bonds. And then last but not least, the hydrogen bonds. Now hydrogen bonds, they're not going to share the electrons equally. Think of the water molecule. Remember I talked about there's a partial positive and partial negative part to that. Now, when that happens, the attractive force kind of pulls them together and forms that hydrogen bond. Now, it doesn't have to be with water. You'll see them happen between different things. A big one's going to be with your DNA bases. They're going to have hydrogen bonds between the nitrogenous bases. They're going to hold them together. They're very weak. They're still strong enough to do what they're supposed to do, but we're able to break them quite easily. And the last part of chemistry, which I think is kind of cool, is how do you think life started? We had this primordial soup, Campbell's soup label right here, because we've been trying to figure out, how did life start? Did it come from another place? Did it just all magically come together? You know, it's one of those questions. One group that tried to address that is the Miller and Urey experiment. So what they did, it's quite eloquent when you think about it, they had this closed network. So what they did is they have all the stuff that they need for the starting elements. So they thought about the atmosphere and like all the elements possible in the Earth's atmosphere and liquid and all that stuff early on. What they do is they have all the gases go through, and they're going to have the water, which is going to mimic the ocean. So they're going to heat up the water, and it's going to go through go through this process right here, and as the water vapor is going to interact with all these different primitive gases. So as the water interacts with these different gases, they're going to mimic the atmosphere and apply some electricity. And then what's going to happen is they're going to have a condenser. Now the water is going to condense right here. And what they're going to do is they're going to take samples from this area right here. Now when they did this, they noticed that they saw some of the macromolecules that we'll talk about in the next couple of lectures start to form here. They saw some of the very primitive forms of proteins right here. So it wasn't here before, but the interaction with the water molecules with this gas formed some of the primitive molecules that are essential for life. So this is a video that kind of walks you through it, and which is very cool experiment. So once again, here's some more review stuff for chemistry, and I'm going to stop it right there.